In this video, I will discuss solving for eigenvalues. Although this is a topic that you would see in a differential equations class, only the knowledge for basic college algebra is necessary. So first off, so for an n by n matrix, a square matrix, lambda is a constant, so this symbol means lambda is in the set of real numbers. Lambda here using just a lowercase Greek L. So lambda is just a number. In an n by n matrix, a square matrix denoted by a capital letter here, x, lambda is an eigenvalue if, here A is also denoting an n by n matrix, ax is equal to a constant times x. So here I have matrix multiplication. A and x are both n by n matrices, and lambda is a scalar, and on the right side I have scalar multiplication. i.e., if you have scalar multiplication, this lambda will be distributed to each of the terms in that matrix. So this is really saying, if I get everything collected on one side, that ax minus lambda x is equal to 0. I could, of course, rewrite that by factoring out the n by n matrix x on the right hand side, and lambda I could not write a minus lambda. That doesn't make any sense because that's a matrix minus a scalar. So I've written lambda I, and that's how that factorization would have worked. Lambda I will be the matrix that is an n by n matrix and has lambda down the diagonal. And so A minus lambda I will be the original n by n matrix that we started with A, and we will have lambdas, we'll subtract lambdas from everything in the main diagonal. And that will be equal, so this equation, that times x is equal to 0. So what I have here, it says the matrix equation, this has a non-zero solution, x, if and only if the matrix is singular. So what I mean by that, you have a product here, something times something is equal to 0, which implies one of those would be 0, must be 0. That's the only way we would get a product equal to 0. This statement is saying the matrix has a non-zero solution x, so x is non-zero, if and only if this matrix does not have an inverse function. So that is if and only if the determinant would be equal to 0. Looking at this equation will provide us with an nth degree polynomial equation, often in differential equations called your characteristic equation, and it will have n zeros. So lambda will have as up to n different zeros depending on if we have multiplicity. So what I'm going to talk here is I'm really reminding you of what we learned in college algebra that could help prepare you for these ideas. Now I don't want you to get too caught up. The one new vocabulary word is eigenvalue, and I will be using lambda, and I don't want those to confuse you. Remember, lambda is just a number. Eigenvalue is what I'm calling that number, lambda. So here is an example of what I wanted to discuss with you. So determine the eigenvalues for the 2 by 2 matrix. Here I've given you a 2 by 2 matrix. A is a n, so it's a n by n 2 by 2 square matrix. And here I've asked you, we must solve for when the determinant of this expression is equal to 0. Now, this equation I wrote in the last slide, and I said that lambda is an eigenvalue if it solves this equation. So we're about to solve this equation. You'll notice I changed the brackets, so I have the determinant of the 2 by 2. Everything in the diagonal, I've subtracted lambda. If you're uncomfortable with using lambda, you can use another letter of the alphabet. But this determinant that denotes these straight bars like absolute value bars, I've taken a minus lambda. This is actually a mistake I'm going to fix really quick. There we go. So I've taken a and subtracted lambda down the main diagonal, and I want to find when all the lambdas where this would be equal to 0. So in the next part, I'm going to expand the left-hand side by multiplying through the main diagonal. So this would be your AD minus BC. So you'll subtract the opposite direction. Since it's negative 6, I have a double negative, so I've added 6 here. I want you to maybe multiply this out, combine like terms, so that you'll get a quadratic. You'll notice the lambdas were both negative, so I have a positive lambda squared. I had a positive 3 lambda minus 4 lambda gives me a negative lambda, and then this should be a positive 6. No, a negative 6, I apologize. So negative 3 times 4 is negative 12 plus 6 gives me negative 6. And so this quadratic equation, you could factor it or use a quadratic formula, but of course this one factors quite easily. That factors into lambda minus 3 and lambda plus 2. Therefore, we had a 2 by 2 matrix. After expanding this expression, I ended up with a quadratic equation. I was able to factor. Since I have 2 unique roots, I have 2 different answers for lambda. So lambda is equal to 3 as well as lambda equals negative 2. So this 2 by 2 had 2 different solutions for 2 different eigenvalues. I'm going to do this next for a 3 by 3. And I just want to remind you, if you haven't seen this before, how to find the determinant of a 3 by 3. Now, and often in college algebra classes, we just have students use a calculator, so you maybe haven't seen this before. To do this by hand, this is a common requirement in a Cal 3 class or differential equation. But to find a determinant of a 3 by 3, we expand a row using cofactors. And you can actually use any row or columns, but for a matrix such as this, so for this 3 by 3, what I'll do here is I look at the first, what I have done on this slide, and this is not the only way to do it, but to teach you for the first time if you haven't seen this, I've taken the term in the top left-hand corner, so 1, and I've simply written that, and then I blocked out, so I want you to imagine just covering this up, 1, 2, 3, cover up the first row and cover up the column. And the reason we're covering those up, so anything that first term was in, you're going to ignore the row and the column. And you're going to isolate the 2 by 2 matrix that is remaining. So this matrix right here, you'll notice I've put it in the straight bars. I want to take the determinant of that 2 by 2. So I've written the first term and then I will multiply by the associated 2 by 2, the determinant of that 2 by 2. So that's what I have here in yellow. You'll continue this, and if you've seen this before, then you've studied this a little bit further. If this is your first time, it may require some additional studying, but in hopes of making this video short, I didn't go into this. So this is a part, here I have a negative 2. What we do is we write the terms from the first row, if you're using the first row, but we alternate positive and negative. And so the 1 will stay positive, but the next term I use would be a negative 2. The next term will be a positive 3. If this was a 4 by 4, the next term would have been a negative term, etc. So that continues. If you're using the first row, that's that pattern. It goes positive, negative, positive, negative, positive, negative. Okay, so I've written the 2. It's negative because I'm alternating positives and negatives, and then what I do again is I ignore everything in that row of the 2 and that column of the 2, and I am left with a 2 by 2 matrix, negative 3, 5, and negative 2, 1, and I want the determinant of that remaining 2 by 2 matrix. And this continues. I would write the 3, so now I have expanded the first row in terms of determinants of the remaining 2 by 2s. I write the 3 and I take the determinant of the 2 by 2 that does not share anything in the same row or column as that value 3. And I suggest you practice this. Don't just take my word for it. You might practice this with a couple, and you can check your work on a calculator. So once I've expanded this, now it's a piece of cake for anybody that knows how to take the determinant of a 2 by 2. Your determinant, this yellow 2 by 2, you'll have 4 minus 4, which would give you 0. For the blue one, we have negative 3 plus 10, so I'll have 7. Here I'd have 6 minus 20, which gives me negative 14. I simply finish the arithmetic, and I get that the determinant was negative 56. And I suggest perhaps make one up and try that on a calculator and see if you could do it both by hand and on your calculator. The reason I was reviewing this is because the next problem I have here, we're going to determine the eigenvalues for a 3 by 3 matrix. So here I have A is given, and we want to solve this equation for when the determinant of that matrix, had that mistake that I didn't see until now, for when the determinant of A minus lambda I is equal to 0. So we will take the determinant of the 3 by 3, and the one change is we'll be subtracting lambda from the diagonal. Now, if you have had some linear algebra or you have taken differential equations or possibly a Cal 3 class, you might notice that there are some shortcuts for this particular matrix. My explanation right now would be more for an introductory student, for a student that was more new to this. So there are some shortcuts for this particular matrix, but what I'm doing right now is really just following what I did in the last step. So here I have the determinant. I have subtracted lambda from the diagonal, and I want to expand this by expanding the left side. So I've taken the element in the first position, the first left-hand corner, and written it, and then the associated 2 by 2 matrix, I have taken the determinant of that. I have 1 minus lambda times itself minus negative 2 times itself, which is 4. So this represents the first. This is what I would have for the first term. The negative 2 here, because that's the second term, and I'm alternating positive and negative signs, I've written 2. And then negative 2 times 1 minus lambda minus negative 4 gives me plus 4, and so this would be that second part. For the third, I've written 2. Negative 2 times negative 2 is 4. Minus 2 times lambda is written here. This, you'll notice if you were to multiply things through. So the reason I like reviewing this with my college algebra students is because it has you practice and develop your knowledge of polynomial equations. So I encourage you, multiply some of this out and try to combine like terms. For this first term, you'll notice you have 1 minus lambda all raised to the 3rd degree. You can use the binomial theorem and expand that. Expanding the 1 minus lambda through, and then multiplying out terms, you should get something like this once I've factored. So I did skip a few steps. What I've done here, and this does take a few minutes, I've multiplied through everything, combined like terms, and then factored. Once I factored again, I was able to get this nice factorization that makes me, or that alerts me, I'm going to have a repeated root here for this equation. So lambda equals negative 1 with multiplicity 2 because of the power 2, and lambda is equal to 5. So I mentioned before, if it's an n by n matrix, you will have at most n unique eigenvalues. Here I have 2 unique eigenvalues. One is a repeated value, and so that could affect, perhaps I'm looking for eigenvectors later, that could affect my eigenvectors. So this result is lambda is equal to 5 and lambda is equal to negative 1 multiplicity 2. Those would be the eigenvalues for this matrix A. Now, if you are just in college algebra, you can certainly stop the video here, and you don't really need to know the next 2 slides, but if you have heard of eigenvectors before, so I'm going to talk a little bit about eigenvectors, and I also want to mention, if you have matrix equivalent matrices, so if you are familiar with row operations and what that means, then that is one of the hints that I was giving on the last slide. There were some shortcuts for that because it was a symmetric matrix, and any matrix equivalent matrices will have the same eigenvalues, and that can sometimes be a shortcut for some if you're familiar with matrices and how they work. For each eigenvalue, the corresponding eigenvector we might denote as xi, and if each lambda is distinct and real, each xi will be linearly independent. The associated eigenspace is a vector space that pairs together your eigenvector with your eigenvalue. I'm going to just show you one example. For the same vector, for the same matrix that we were just working with in the 3 by 3, we had two eigenvalues. I'm only going to show you how to get an eigenvector once. What I've done here is I've taken that matrix and I went ahead and I plugged in 5 for lambda. So I subtracted 5 from the diagonal to get this matrix. Just using the first row, and you could use any row, using the first row, that first row, if we were using x, y, z, then I would have negative 4x minus 2y plus 2z, and because of my setup earlier, it equals 0. To get an eigenvector, you could really plug in anything for x and y. What I have done is I've plugged in 1 for x and 1 for y. When I do that, I get negative 6 plus 2z equals 0. Solving for z, I get 3. This would be an eigenvector for the eigenvalue 5. This is not the only way to write this eigenvector. If you've had Cal 3, there are many different ways to write a vector that would span the exact same vector, a vector that would span the same space. And so keeping that in mind, this has multiple ways to write it. I could have used another row, and so this is not the only answer. But that just gives you one example. For lambda equals negative 1, I'll let you try. Because that had a repeated root, there are some other ideas involved, but for lambda equals 1, here I plugged in 1 and 1 for both x and y, and I got 0 for z. Here I plugged in 1 for x and y for 0 for y, and I got z equals negative 1. These vectors span different directions, so both of these, because we had repeated root, I would need two linearly independent vectors, and these will be linearly independent, so they are both associated with that eigenvalue. Alright, I will end this video. Let me know if you have questions. This was just to discuss eigenvalues and eigenvectors. Thank you.